On May 12, 2022, astronomers released the first picture of the supermassive black hole lying at the center of the Milky Way. It's located on the border of Sagittarius and Scorpius constellations, and it's called Sagittarius A star. This supermassive black hole is 27,000 light-years away and subtends an angle of just 52 micro-arcseconds in the sky. So imaging this black hole is like pointing the telescope at a donut-sized object on the moon. It took several decades to master the technique involved in producing this image of the black hole. It's a significant milestone in radio astronomy and computational physics that lies at the heart of modern research. But this interesting story began about 100 years ago, when radio astronomy hadn't even started. So what happened back then that led astronomers to focus their instruments in this region of the sky? How is this image different from the supermassive black hole of M87 released in 2019? And most importantly, why is this image so important for physics and astronomy? The story began in the 1930s when Carl Jansky, now considered the father of radio astronomy, discovered the first radio waves coming from space. Jansky joined the research staff of Bell Telephone Laboratories in 1928, where he was assigned a challenging task. Bell Labs wanted to investigate atmospheric and ionospheric properties using shortwaves, 10 to 20 meters, for use in transatlantic radio telephone service. As a radio engineer, Jansky was asked to examine intermittent static sources that might be interfering with a radio voice transmission. To do so, Jansky designed and built a unique antenna system, dubbed Jansky's merry-go-round. After rigorous analysis of data collected over many tedious months, Jansky identified 3 static types: a weak signal caused by distant thunderstorms, a more powerful burst due to local thunderstorms, and then the third type of burst, producing a steady hiss. This third signal was one of the strangest things ever recorded. Jansky suspected that the signal originated in the center of the Milky Way galaxy, making it the first known detection of an extraterrestrial radio signal. Furthermore, it appeared strongest in the constellation of Sagittarius. He wanted to continue investigating the mysterious cosmic signal by building a 30-meter dish antenna. However, Bell Labs considered the task assigned to Jansky completed and moved him to another project. But Jansky's observation of the strange signal didn't go unrecognized. Soon, astronomers connected this bright radio source with the galactic center. In 1974, 2 astronomers named Bruce Ballack and Robert Brown used the U.S. National Radio Astronomy Observatory's radio telescope to study the Milky Way center. They found a small core in the region powerfully emitting radio waves. Since it was the first such radio source found in the constellation of Sagittarius, it was named Sagittarius A. The discovery of a radio source at the center of our galaxy was deemed very exciting, and as the excited states of atoms are denoted with asterisks. In 1982, Robert Brown named it Sagittarius A star. Further observations confirm that Sagittarius A star was a part of the galactic center and not a distant background object. Moreover, it was found to have a mass around 5 million times that of the Sun, clumped into a tiny volume of space. All these parameters pointed to this region being the Milky Way's nucleus. But one question always remained open. Was Sagittarius A star a supermassive black hole or something else? Astronomers could not observe Sagittarius A star in the optical spectrum because of the effect of 25 magnitudes of extinction caused by dust and gas between the source and Earth. To find an answer to this question, 2 teams led by Reinhard Genzel and Andrea Ghez started studying the infrared radiation coming from the Sagittarius A star region in the early 1990s. They discovered dozens of stars within 0.1 light-years of Sagittarius A star, called the S stars. One of these stars, S2, was found to have an orbital period of only 16 years, and it came within 17 light-hours, or 120 times the Earth-Sun distance, at its closest approach to the central radio source. After studying the distances, speeds, and orbits of S2 and several other stars in this region for years, researchers concluded Sagittarius A star to contain a mass of 4 million suns within an area of space equivalent to the size of our solar system. This configuration was possible only if Sagittarius A star was a supermassive black hole instead of a cluster of dark stellar objects or a mass of degenerate fermions. After years and years of continuous observations and data analysis, Genzel and Gez confirmed the presence of a black hole, Sagittarius A star, at the center of the Milky Way. The result was announced in 2008 and published in the Astrophysical Journal in 2009. Genzel, the research team leader, said the study has delivered what is now considered to be the best empirical evidence that supermassive black holes really exist. The stellar orbits in the galactic center show that the central mass concentration of 4 million solar masses must be a black hole, beyond any reasonable doubt. Genzel and Gez together received 1/2 of the 2020 Nobel Prize in Physics. The image of Sagittarius A star was released on May 12, 2022, for the first time based on radio interferometer data taken in 2017. It further confirmed that the object is indeed a black hole. But technically speaking, it's a picture of the accretion disk around the horizon of Sagittarius A star that took 5 years of calculations to process. And the data was collected by 8 radio telescopes at 6 different locations. Around 6,000 terabytes of data was produced, and if it were printed on paper, this stack would have reached the moon. The image is quite similar to the one released 3 years ago, when the Event Horizon Telescope imaged the supermassive black hole at Hart Messier 87, called M87 star. However, there is a lot of difference between the two black holes. To begin with, M87 star is at the center of a gigantic elliptical galaxy, while Sagittarius A star is located in the middle of a spiral galaxy. In addition, M87 star is roughly 1,000 times more massive than Sagittarius A star and lies approximately 54 million light-years away, 2,000 times more distant than our galaxy's supermassive black hole. Most interestingly, M87 star is active and has a plasma jet shooting 5,000 light-years away from it. Sagittarius A star isn't active, but astronomers have observed 2 bursts of activities in the past decade. On January 5, 2015, NASA reported observing an X-ray flare 400 times brighter than usual, a record breaker from Sagittarius A star. According to astronomers, the unusual event may have been caused by the breaking apart of an asteroid falling into the black hole, or by the entanglement of magnetic field lines within gas flowing into Sagittarius A star. On May 13, 2019, astronomers using the Keck Observatory witnessed a sudden brightening of Sagittarius A star, which became 75 times brighter than usual, suggesting that the supermassive black hole may have encountered another object. Despite significant differences between the black holes, the similarity of the images shows that it's gravity that dominates close to the event horizon. Our galaxy center is the perfect region to test Einstein's general theory of relativity. The high velocities and close approaches to the supermassive black hole make the S stars helpful in establishing limits on the physical dimensions of Sagittarius A star. Among all the stars, S4714 is the current record holder of the closest approach to the black hole, at about 12.6 astronomical units, almost as close as Saturn gets to the Sun. Because of its vicinity to the black hole, It travels at about 8% the speed of light. As stated earlier, the first estimates of the black hole's mass were made by studying the orbits of these S stars, and the number came out to be about 4 million solar masses. A black hole's shadow is directly proportional to its mass, and when astronomers calculated the mass by analyzing the image, it perfectly matched the theoretical values. Hence, with this image, Einstein's general theory of relativity has passed yet another rigorous test with flying colors. The James Webb Space Telescope will join forces with the Event Horizon Telescope in the future. During Webb's first slate of observations, astronomers will use its infrared imaging power to address some of the unique and persistent challenges presented by the Milky Way's black hole. The Sagittarius A star research team plans to apply for more time with Webb in the future years to witness additional flaring events and build up a knowledge base, determining patterns from seemingly random flares. Knowledge gained from studying Sagittarius A star will then be applied to other black holes to learn what is fundamental to their nature versus what makes one black hole unique.